Now we go with the next talk, that is Catalina Albornoz. Catalina belongs to PennyLane, and she's going to talk about how the company works on quantum computing and how her experience on that is. So, Catalina, thank you very much to have you here as well. So sorry for the late notice on that, on the seminar. That's all yours. Thank you very much, and please go ahead whenever you want.
Thank you very much, Alberto, and everyone. I hope you have heard of PennyLane before, and if not, then you're going to enjoy today. I'm going to talk about different topics, and yeah, I don't know if I belong to PennyLane. Definitely, PennyLane doesn't belong to me. It belongs to everybody. But I like I like how you mentioned that. Let me now share my screen.
Yes, I make you a host. Yes, thank you.
Perfect. Okay.
We can see your screen. Yeah.
Yes. So I don't belong to PennyLane, but maybe I do. Maybe I do. I work for Xanadu. Xanadu is the company that leads the development of PennyLane, but PennyLane is an open source Python package, right? So you can use it, you can find it in GitHub, get a fork, and even create your own startup if you want using PennyLane on top of PennyLane. Several startups have done that. I am an engineer, so I don't have a physics background, but I do work in quantum computing. I was specialized actually in control systems. At that time, I didn't even know that quantum computing existed. I worked in several different things, energy efficiency, and then I joined IBM. And at IBM, I discovered quantum computing, and I became the first IBM Quantum Ambassador in Colombia. So I am from Colombia. But right now, I am in Toronto. I'm working at Xanadu, which is a very important quantum computing startup in the world. We recently, last year, we announced the first quantum computer capable of quantum computational advantage. It was put on the cloud for free, it's still there. So I'm going to mention a little bit more about that, about Xanadu, and about like what we do in the PennyLane community. So I work as a quantum community manager. And this title doesn't say much really, but I work with people who want to do quantum programming and quantum research. So I help them navigate the breadth of resources that we have. So I work a lot with academics when they have courses and they want to include something around quantum programming. I help them show around the variety of resources that are available, help creating new resources, new events as well. So I'm going to tell you about a real amazing event that is starting on Monday. And Alberto mentioned that you might be interested in learning about applications and the research we do here. So we're going to go fast. You can interest me and ask questions, of course, and I will try to make up for the time that we started late, right? So I already mentioned a little bit of what we'll do. We'll mention about Xanadu and photonic quantum computing, differentiable quantum programming, which is, it's very important to understand PennyLane. And then I will go deep into PennyLane. And finally, I'll mention about the research and opportunities of where to learn more. I think that's the key part, because everything else you might forget, and that's okay. You'll get an overview today, but the important thing is to know where to go next, what to do after this talk. So hopefully you will have that in mind. You will listen to everything, try to get a scope of what we do, but at the end, focus on how to keep learning. Yeah, so I mentioned a little bit about who we are. Being a young company is really cool, and this is something that hopefully you will be able to find in your future and choose. Not either startups or big companies are for everybody, so you need to find the right balance of freedom, of responsibilities, the right kind of environment where you thrive. So I personally love this environment where you have access to rapid development, where you can do things really quickly, make an impact on whoever your user is going to be, right? Whether it's internal or external. Our mission is at the core of what we do, right? We have it in every presentation that we give, and everybody knows it by heart. It's printed on one of the walls just at the entrance of the office. We want to build quantum computers that are useful and available to people everywhere. This forces us because we have it at the forefront of everything that we do, this forces us to choose, to make good decisions. You will always need to prioritize what you do. And by having our mission at the forefront of everything that we do, then we can prioritize and make sure that this becomes true. This means working on the hardware. So we are experts on integrated nanophotonics, how to use photonic chips to do quantum computing. We are experts in how to integrate and put those systems together, because this is not going to become one huge chip. This is a lot of chips that are going to be interconnected and that perform some tasks together. And people need to be able to use them, and that involves a lot of platform and software. So we have Xanadu Cloud, for instance. We have a great team working on how to make us the right place where every time you want to do quantum computing, you will go to Xanadu Cloud. And of course, the research is very important. We do research both on fundamental theory and applications. And this is what makes us full stack, right? We focus on our mission through the different steps in the stack. There are certain benefits in having photonic quantum computers. First, you can network them and build several modules, right? You can use established technologies that are already a thing in the telecommunications industry, such as silicon and fiber optics. And our architecture allows us to have error correction, right? So it makes it harder to make the first qubits, but those qubits will be better, and the scaling will be easier. You may have heard or not that photonic quantum computers work at room temperature, and that is 99% true. Almost everything works at room temperature, but for us, the measurement, so we use with pulses of light, but the measurement does need to be cooled down. In our architecture, we use some devices that count photons, and that part is cooled down. So it is still a huge advantage that you don't have to put everything into a fridge. So we don't need a fridge that is the size of a room. That's not necessary, because we can have almost everything outside. We can do a lot of things outside, and just having the detection, just the measurement inside of the fridges, that is very useful. We have a roadmap and several key steps in how to get to these fault-tolerant quantum computers. Us and everybody is looking to build these computers. So we are right now in the middle of the slide. The first, or maybe some earlier generations of photonic quantum computers that we have had are the X series quantum computers. Our X8 chip is probably the most famous because it's the first photonic quantum computer that was put on the cloud. It's still on the cloud, available for everyone. We also have Borealis. Borealis is not a chip. So, I mean, here the size is not comparable. This X series chip is really tiny, while Borealis takes up an entire optical table. And there are several key elements about Borealis. So first, it's available for free on Xanadu Cloud. So you can go on weekdays on Toronto working hours. You'll see the working times on the website on Xanadu Cloud, but it is available for free for people to do research. It's important for us to have everything be available for people. So being able to put this photonic quantum computer capable of quantum advantage, quantum computational advantage, is huge. It also forced us to develop key technologies for the future. So the goal wasn't to have build Borealis and then turn it into a chip. That's not the goal. The goal was to force us to develop some technologies that are necessary for our fault-tolerant modules. So some of these technologies and ideas are using the time domain, not the space. So we don't have a lot of parallel modules like in the X chip. You'll see there's like a top line here, and then some medium ones and a bottom one. There are like 4 spatial modes. Here you have a single fiber optics where you have temporal modes. You have some loops, basically some coils of fiber optics, which allow you to keep your, the equivalent of your qubit. This time it's a qubit mode, but it allows you to keep it there for a certain amount of time, long enough that it will wait enough time to be able to be entangled with other qubits. And then, well, you can have, we have a demultiplexer, which is necessary to bridge a gap in the frequency from the generation of the qubits, Q modes. They're squeeze state qubits, you can think of them as that. And then you have the detection. So there are key elements here, such as developing those loops of fiber optics, the concepts of time domain multiplexing that are important in order, like necessary for fault-tolerant modules, right? Borealis, in the experiment that was published in Nature, was able to solve a task in 36 microseconds, a very specific task, in 36 microseconds, and it would have taken a classical computer 9,000 years to solve this same task. Now, what is a task? It's Gaussian boson sampling. As far as we know, this is not useful for anything. We would love for it to be useful for something practical, but as far as we know, it's not, right? So this is important to take into account. It's not like you can take Borealis and run your quantum machine learning algorithm here. You can use it for research, but Gaussian boson sampling in itself, as far as we know, isn't useful for practical applications, right? So we're not turning Borealis into a chip. We're using key technologies that were needed to develop Borealis and using those technologies for our future modules. So right now we're focused on building our fault-tolerant modules. And so if you follow us on social media, we will definitely be updated of like when we get this, right? The way our fault-tolerant modules work, in just a few words, you first have to prepare your states. These are GKP qubits that we will be using. They are, however, generated probabilistically, not deterministically, which means that you cannot generate them with 100% probability. So you need a component number 2, which is a multiplexer, which basically pulls those states that were in fact generated. It pulls them into the next step, which is the stitcher. So imagine it's like you want to throw a coin and hope that you get a heads, right? You have 50% probability of getting heads. But in component number 1, if you have 100 coins, you're increasing your probability of getting at least one head. And your component number 2 is pulling out those results from the coins that actually did produce a head, and then stitching them into component number 3. This type of computation is different to the one you probably have heard about or seen on the internet. This is measurement-based quantum computing. And this means that your operations, your gates, so when you have a circuit, you're applying some gates to your circuit, this will happen at the moment of measurement. The measurement is very closely related, like it's how you do your computation, it's how you do your measurement, right? And so in the stitcher, you can create an entanglement of your qubits. You entangle them in certain ways so that when you perform your measurement, you'll get an output of your computation. So you don't have to have your states being like active forever. You know, the coherence time here is not so critical because you can, in parallel, entangle more qubits in component number 3 in the stitcher. And then for a few layers later, like X amount of time later, you just measure it, right? And you can do this continuously. You stitch, you measure, you stitch, you measure. And so this is very useful if you want to make large circuits, deep circuits, for instance. Okay, I'm going to make a pause here. Do we have any questions so far? Or I don't know, Alberto, if you want to keep them for the end.
No, it's absolutely fine. I mean, usually what we do is that if there is any question, they can interrupt you or they can put in the chat, and then we will collect all of them at the end. But it's absolutely fine. I
Okay.
also really appreciate when I usually speak like you, that if there is any question, just interrupt or raise the hand. But as of now,
Mhm.
it's not anyone. But please, the audience, please go ahead if you have any question.
Yeah. Come on. It's better if you ask questions about the hardware now, because I'm not going to talk about the hardware later. No?
In fact, if I may ask, Catalina, I saw that you are going to have more or less the same. I mean, it's not the same roadmap, of course, like IBM, but the idea is to parallelize different quantum circuits, right? Instead of developing a really huge quantum circuit with a lot of qubits, is to parallelize all of them and then combine them, right?
That's right. That's exactly right. So I didn't focus a lot on this last part of the slide, but that's where this happens. Once you build one module, then integrating several modules together is easy. Because we work with photonics, you work with light, and you have fiber optics and everything. And networking these modules is fairly easy, right? So then you can think of building a data center, either purely quantum or combining it with classical. It is like, if you someday come to Xanadu, you will see that our systems fit our current systems, except for Borealis, could fit in a classical server rack. So it's something that is modular and scalable, right? You can build them one next to the other. You can build these modules with a few logical qubits, but then integrate them together into what would be like a huge quantum computer. You can think of it that way. Great question. Oh, I see that there's a question in the chat.
Yeah,
Is
there
it
is another one.
possible
Yeah, go ahead,
to use
please.
the Xanadu platform for testing or experimental using academic users? So everybody is welcome. So you usually don't have to wait a long time in the queue, because this, like Borealis, everything runs very fast. X series too. You cannot do anything. So that's very important. It's not general purpose. It's not universal. Not universal. So you cannot do absolutely everything. But yes, you can run there, and it's usually pretty quick in the working hours, the hours that it's online. It's usually very quick. So you can absolutely use it for testing or experiments. Yes. Something to note is that for using the X series and Borealis, you will need to use a software called Strawberry Fields. Strawberry Fields was designed to interface with our NISQ quantum computers. But for our fault-tolerant modules, because of the way it works, and you perform your measurements with a gate-based model. So for the Borealis and the X series, you use the continuous variable quantum computing. So that's why you use Q modes, you use squeeze states and squeeze states. But for our fault-tolerant module, you use the gate-based quantum computing. So the way you interact with your quantum computer will be through the normal gates that you're used to. So you can use PennyLane, for instance, for our future fault-tolerant modules. The goal is that you can use PennyLane, and you don't need to learn a different kind of quantum computer, which is gate-based quantum computing. And you won't need to learn Strawberry Fields as you do now. So now you will need to learn a new kind of quantum computing and a different software if you want to use X series and Borealis. It is totally possible, and we do have like educational resources, and I can help you answer your questions about that too. And you can use it for research. But just this word of caution, right? If you want to use our future modules, it's better to focus on learning PennyLane. If you want to use our current hardware that is available on the cloud, or NISQ hardware, then Strawberry Fields is a better option. But yeah, great question. Okay, I do hope you...
Catalina, yes. I have a question related to the photonic, the last slide.
Yes. This one?
Oh, the last.
This one.
This one. Related to the photonic device, how do you manage to integrate this? I mean, it is a small device, or you use fiber optics. It's not in a small. How do you manage? Because photonic device, you have to have lasers and different parts.
Good question. So the lasers are the sources, right? The sources of light. You then squeeze that light and you get like the equivalent of your, well, it's squeeze states, right? Q mounts. This will be the input for, you know how, and actually, I think this is a better slide for that. You see in the first component that you have some like loops and some, I'm gonna say like some waves, right? You have some loops and some waves. These represent squeeze states and GKP qubits. So your lasers will be needed for component number 1, where you generate those squeeze states. The good thing is that you can generate a lot of squeeze states using the time domain. You can with a single laser, or maybe like I don't know the details. I don't work in the hardware side of things. But the lasers will be needed only for component number 1.
It is silicon-based devices for the squid.
I'm sorry, somebody has their mic open and I'm hearing some noise. I don't know. Yeah, okay. So I think Oscar, you were asking the question.
Yeah, my question is a silicon-based device for making the squeeze, or how do you know something about the material?
For the squeezing, it's with a crystal. Now, currently, wait, for Borealis, it's with a crystal. But yes, here you can do it when on a chip. Actually, maybe, let me see if I have a good picture. I don't have a great picture. Here, probably in the X series, it's a good example. The first thing you see in the X series is a tiny loop, like a kind of a circle. You see a circle? Those are resonators. Those allow us to do the squeezing. So the blue circles, the resonators that allow us to do the squeezing, to create those squeeze states on chip.
On chip, okay, thank you.
Yeah, for Borealis, it's a crystal, but for the X series and I believe for our fault tolerant modules, it will be on a chip. Great questions.
Yeah, we
Okay.
have one more question related to the hardware. Sorry, Catalina. What are the limitations of photonic quantum hardware? I understood the connections between the qubits are more difficult. Is it so?
Can you repeat that question? So,
Yes.
sorry.
What are the limitations?
Oh, I can see it there.
Okay.
Connections between qubits are more difficult. Actually, no. That's the easy part. Because everything it's on a chip. It's easy to connect the qubits. And in superconducting, for instance, it's harder because if you connect them, you can get like crosstalk, which is something you don't want. But if you don't connect them, then you cannot do multi-qubit gates. Here, the connection between qubits is actually a good thing. There are some limitations. For instance, there is loss because you're interconnecting, and actually, this is a good example. In the first image, you see, well, I don't know if you see very well, but there's a fiber coming from the left, there's a tiny chip in the middle, and there's some fiber on the right. Connecting that and aligning that it's important so that you don't lose your light, right? Losing that light is a problem. And so that's why we have a team that works on packaging, for instance, on making sure that everything is very well aligned and like stable, right? We're thinking of the future of making a lot of these modules. So scaling, you need to think about stuff like this. There are engineering challenges. I mean, the theory works, and our milestones, what we have achieved so far, shows that we can achieve like the levels that we need. It's just it's a matter of science and engineering to get to build this in practice, really. I hope that answers the question. I see that somebody else asked, what technology is used in the photonic chips? What is the advantage of silicon photonics over the other ones? I mean, this is silicon nitride. I guess one advantage is definitely that the world is expert in working with silicon, and it's widely available. It's not a resource that we think it's going to run out of, we're going to run out of soon. So that's something good. Aside from that, from an engineering perspective, I don't know. I don't know if there is a scientific reason to use silicon chips over something else, but I know they're good for putting light into them. I know they work. They work, and it's a very established technology. So I don't know if there is a scientifically better option, but you need to think about a lot of aspects, right? I cannot think of something that would be a better option than silicon chips. Those are great questions about the hardware. I will go forward because we have limited time, and I want you to be able to ask questions about a lot of things. So now we'll talk about differentiable quantum programming. I'm assuming that everybody is aware of quantum circuits and quantum computers. Alberto, maybe you can like clarify, maybe if we need a refresher of something, but can I talk about quantum circuits comfortably?
Yeah, you can, but I think the students should already know most of it, so that's up to you. If you want to do a quick refresh, it's fine, but yep.
Okay, great. So if you do not know something, do please ask. I don't want you to get lost. Okay. So our quantum circuits are basically linear algebra machines, right? We have some initial state, which usually starts in 0. We have some gates, and then we have some measurements. Our gates are just matrices, right? And those matrices can be parameterized. So here we have some Y rotations, and these Y rotations take some angles. These angles can either be fixed. I can say for qubit 1, this is a Y rotation of pi/4, and that's it, and I'm never going to change that. Or I can say, actually, this is an angle theta, and I will perform several iterations where I will modify my circuit and find a new value of theta that will give me a different measurement, and that will result in a different value for my circuit, which will mean something to me, right? I will compare it using a specific cost function or something, and it will have a meaning for me, and that will allow me to decide how to change that variable parameter theta. So some key element in variational algorithms, which are very used today and like very interesting to explore for different purposes, whether it's on quantum chemistry or quantum machine learning or different areas. Variational algorithms are an interesting tool that we have in our toolkit, right? The first thing you start with is an ansatz. So what is the choice of gates that I have in my quantum computer? Some of them will be fixed and some of them will not. You will have a cost function, and your cost function will depend on your problem. So you can have a generic ansatz. You can say it's just a lot of entanglement stuff. But then your cost function, it depends on what you actually want to do, what you want to compare to, or what do you want to achieve with your problem. And you also need a way to update those parameters theta, right? If you just guess random numbers for theta, it's going to take a long time. If I give you a circuit like this and tell you I want my output to be 0 and 1, find the values of theta, it will take you a lot of guesses to actually find the right values. So finding a smart procedure to find the right value of theta, I mean, that's the ideal, right? You can think of your circuits as they are a function, right? They have some inputs and they have some outputs, right? And at the end, you will calculate something like an expectation value. Here we call it V. It will be something like an expectation value, which is a function of the parameters that you have in your circuit. Now, if you are aware of how classical optimization works, in classical optimization, you use something like gradient descent, for instance, or different methods to find the right direction in which to modify your theta, right? And so gradients Gradients are the direction of maximum change in your function. If you imagine your function as it being a mountain, and you want to go to the bottom of the mountain, you will think, okay, intuitively, I will walk downhill, but from a mathematical perspective, downhill, the steepest descent will be the direction against the gradient, right? Because the gradient is the direction of maximum change in your function. And so this is just an example of how you would find a way to change those parameters, right? To find a procedure to change the value of those parameters, which will change your function, and so your cost function. If you are doing something like quantum machine learning, right? So what does it mean, quantum machine learning? First, you will need data, right? If you don't have data, it's probably not machine learning. It's probably something else. It could be optimization. And using that data, you will try to find a pattern. You will try to find the underlying model in your data. Say, for instance, you want to guess if a student will pass or fail a class. And the only information that you have is the grade after the first exam or the first homework. How will you be able to predict how well the student is going to do it, whether or not they're going to pass well? That would be a classification problem because you're classifying the students into two classes, pass or fail. But you could also decide, actually, I'm going to do a regression and try to predict the actual grade of my student at the end of the class, depending on the grade of the first homework. So actually, I don't know if you do a lot of practice in your studies, but maybe this is a like a test example that you can do. Try to.
Just to let you know, Catalina, sorry to interrupt you, but yes, they will in the next subject, in the next practice subject. They didn't do it yet, but they will do in the next practice subject.
Okay, perfect. That's great. So quantum machine learning is this interesting area where you have the characteristics of classical machine learning. So you have a lot of data and you may want to do something like classification or regression. And you have some functions and you have some optimization and training procedures and cost functions. However, the difference is that here you don't have say a neural network, right? What you have in the middle from your data to your output, these are quantum circuits, right? So these are special kind of functions which are different to your classical functions. And you can think of quantum machine learning from a double perspective. Either I have classical data and I want to use a quantum computer to try to enrich my model and to explore something different, see how a quantum circuit will help me model my data, unlike a classical network or some other classical tool. That is one option, classical data, quantum computer. Some other option is, actually, I have quantum data, right? So I could have something like a chemistry problem where the data in itself is quantum, right? This is one reason why chemistry problems are so interesting for quantum computers, because the underlying problem already has all of these quantum properties that we don't have to mathematically spell out because they are exhibited by our quantum computers. So that's an interesting question as well. Maybe we can use classical techniques. Maybe we can even use classical techniques to try to do machine learning on quantum data, or even try to use classical computers to improve quantum processes and quantum computers. So quantum machine learning has a lot of different ways of looking at it. But something that is key is that you will need data and you will need a cost function or something that you will need to optimize at the end. And in the middle, you can have a quantum computer, which uses a unitary or a function of some parameters. And something that we usually don't ask ourselves when we do machine learning on classical computers is, how do we actually calculate those gradients? How do those training procedures actually happen? So I'm going to make a tiny pause here. It's a good moment to ask questions about what I have mentioned before, but also give yourself 30 seconds to think. How do the gradients are actually calculated on a classical computer? And would the same thing be possible on an actual quantum hardware? Can we find the gradient of a quantum program, and how? Because it's a very different kind of computer. It's not a classical computer where you can program everything with ones and zeros, right? The hardware itself is different. So how do you find the gradient over quantum hardware? So think of this question for a couple of seconds, and if you have questions about something else, this is the right moment to ask them. Okay, so hopefully I've confused you enough right now that you're thinking, what do you mean? What do you mean that you calculate a gradient on actual quantum hardware, right? Yes, it's not obvious because we're used to being able to get away with doing anything on a classical computer. But if you work on actual quantum hardware, you cannot do backpropagation. On actual quantum hardware, you cannot do that. You can do something like finite difference, right? But finite difference leads to errors because it's not an analytic something, right? So if you want to train with gradient descent, you need to be able to use gradients or other gradient-based methods, right? There are many methods and not all are gradient descent. Not all of them are gradient-based. But if you want to use gradients, you need to be able to do them on actual hardware, right? And so at Xanadu, we have thought about this question. And the software that we built, PennyLane, is based with this question at its source. How do we do differentiable quantum programming? And we came up with, we didn't come up with, okay, how do I explain it? We introduced parameter shifts at the core of the software, right? So we derived parameter shift rules, and the parameter shift is a way to get gradients from shifts in your actual function. So this will look a little bit like finite difference, but it's not the same. Let me explain how this works. You have a function, right? F. You want to find the gradient of the function. Say you have your mountain and you want to find for a specific point, the direction of maximum change in your function. Now, I can run my function, like I can calculate the value of my function for a certain parameter, and I can shift that a little bit and find the difference between that. You often actually have a coefficient multiplying this two. So I can find my function and on a certain parameter and a shifted version of my function, and I can find a gradient. Unlike finite difference, because if you remember finite difference, this shift has to be very small. In the parameter shift rule, this shift does not have to be small. This can actually be a large shift. And this is a very specific shift. It's not any shift. For each function, you can find a specific shift that will give you the gradient. And so when you have something like the poly gates, so the X gate and the Y gate and etc. rotation gates, you can actually find a formula, and we have it coded into PennyLane, for instance. You can find formulas that give you the value of the gradient depending on certain shifts, a certain shift in the value of the function, right? And remember that your function is your quantum circuit with a specific gate. You don't have to now think that you have to find those shifts. You don't have to start guessing those shifts. We will calculate them for you. But it's something that is interesting to think about. Finding gradients on classical computers is obvious, it's easy, but not on quantum computers. On simulators, yes, you can do backpropagation in a simulator and it can help you learn a lot of things. We often work with simulators. But when you work on actual hardware, and if you want to do training, it's very useful to be able to do gradients, and you will need different methods, such as gradient descent and the parameter shift rule. So hopefully everything after this will become easier, right? So this is the hardest part of the talk today. Everything else becomes a little bit of a recap and it becomes easier. So there are some important concepts that are useful to know, like assets, I've mentioned it, embedding. So when I talk about embedding, I mean that you input some data into your quantum computer. That's encoding or embedding. How do I put my data into my quantum computer? It's usually a task that requires a lot of time. It's usually a bottleneck and something where extensive research is still needed. You have your parameters, which I call theta here. You have a cost function. So here you can see an image of an example of what could be a cost function. You will often hear something about a loss function, which is similar. It's a technicality, really the difference. You will hear about gradients. Gradient is, again, the direction of maximum change in your function, and gradient descent is a method that allows you to calculate a new value for your parameters. So this smart way of finding the new version of your parameters using gradients. And of course, optimization, like this general thing that will allow you to find those minimum values in your functions, which is usually something that you want to do. Now, why would you use quantum circuits? Well, first, you can increase the capacitive representation of your models. If you have a classical model, you're sometimes limited to a certain space. And by using quantum computers, you can extend that. So from a fundamental research purpose, it's very interesting. And in the future, hopefully this will lead to better or faster training. So it's not always about speed. So it's also sometimes about getting to a better level of precision. Sometimes it's okay to take hours, to take a long time, but if it can lead to a better precision in certain applications, that can be key. So let's think about in the long term, not only having our algorithms be faster, but also if they take longer time, but allow you to get to a better result, that's also valid, and that's a good result to get to. PennyLane is a tool. PennyLane is a Python package that is designed with differentiability at its source and with openness. This is again, like a core thing of who we are and what we do. It's Python based, so it's easy. Hopefully all of you know Python. It's open source, and we are huge in the community. It's something we welcome, and like my job is to help people in the community, right? Whether it's in academia, industry, enthusiasts from everywhere. We welcome and value contributions, and not only in code, but also in other terms. Contributions in different ways are very encouraged and valued. Differentiability, again, like at its core. So this is why I mentioned differentiability before, how important it is. And it's a key something, right? A key element in PennyLane. And modularity. So I will talk more about what modularity means and why this diagram has some green and yellow or orange squares, right? So in PennyLane, we have Q nodes. Q nodes are something that represents the quantum part of our circuit, of our programs, right? We have programs in Python. So you can imagine a normal Python function, a normal Python program. And we have special functions where the only thing you do is you decorate it, you add one line on the top of your function, and that will attach a quantum computer or a quantum simulator, a device, to your quantum function. So that will turn it into a Q node, right? You have a device, you have a Python function, and you have this one line of code which connects it to and turns that function into something special where you do quantum stuff. So your Q nodes, which is here denoted in this green box, receive some inputs. And inside you can have some gates, which take some parameters, right? And finally, they output a classical output. So that's why everything that is quantum can be contained in your Q node, and you can think of it as a black box a little bit, or a green box in this case, a green box that receives some inputs, parameters, and extracts an output. And you can connect it, because everything here in red is classical. You can connect it to classical frameworks and a lot of tools that you already have. And everything that is quantum can be contained inside of the Q node. We are framework and hardware agnostic. And this is very important. So remember, PennyLane is a Python library, and it allows you to connect with different kind of providers, both of hardware and simulators. So you can do a program on PennyLane and leverage the tools that we have and run on an IBM Quantum computer, for instance. Running on Xanadu computers, it requires a little bit more knowledge to understand the gates, right? Because the gates are different. It's not a Hadamard and a CNOT anymore. They're different gates. So that's important to take into account. If you're running on an IBM computer, you will need your IBM key, like your API key. And you need access to the other providers. But if you already have access, you can just program on PennyLane and run your programs on the different hardware providers or simulator providers. And if you already have programs that use classical SDKs, you can connect with them too. So we call these interfaces. So for this right-hand side, we interface with TensorFlow, NumPy, PyTorch, and DAX. You can have a TensorFlow interface and run on different hardwares or simulators as well. We also partner with like several providers in different ways. We have a very strong partnership, for instance, with AWS and NVIDIA. You can run our programs on NVIDIA GPUs, and you can run on AWS Bracket. And we partner in several different ways. For instance, they're sponsors of QHack, which is our signature event. It's the largest hackathon. It's starting on Monday, actually. So if you haven't registered now, the only thing I ask for you today is to go to qhack.ai, QHACK.ai, and register now. Hopefully also share with your networks, with your friends, with your colleagues, with the university, because this is a really great opportunity to be able to engage with the community, learn from incredible speakers, and maybe even win amazing prizes. We have really over $100,000 in prizes. How does this like network notability and how do these interfaces work? Basically, it feels very natural. PennyLane does the heavy lifting for you. So you just need to learn how to create your circuits and how to embed the data and extract the measurements to be able to connect with your classical frameworks. You will see a lot of people who use PennyLane because it's intuitive, and also because we have a lot of like things that make it easy for you when you have quantum programs. If you want something that is closed like a black box and you don't need to tweak at all, you can have it, but usually you will want to explore and evolve and try different embeddings, for instance, right? So we have templates, which are basically these kind of functions you can call, and you can say, this is my data, and I want to have a specific ansatz, right? So you can have a specific ansatz that will help you embed your data into your quantum circuit. You can like find different ansatz, like both for the embedding, but also for the part where you have your parameterized circuits, right? And it will make make it easier to create your optimization programs for variational circuits. And then at the background, it's doing automatic differentiation. So you can, in the end, have hardware computations. So if we focus on the right-hand side image, you have these green boxes, which can be your Q nodes running on different hardware providers or software simulators as well. And in the middle, you have some classical processing, and you can connect everything together. These are some examples of, these are PennyLane simulators that come, when you install PennyLane, they already come within PennyLane. When you use PennyLane, they're already there. So default qubit it's like a basic one. Default mix is for when you have mixed state. So when you have noise, you will need to use default mixed. Default Gaussian, if you're using photonic systems, for the most part, you probably won't need it unless you want to dedicate to hardware research. For the most part, default Gaussian, you won't need it. Lightning qubit is my personal favorite because it's very fast. It's written on C++, and it will make your life easier. You can run big circuits with this. It depends on the size of your machine. So if you're in a laptop, you probably will start having problems at limits of about 20 qubits. But if you have Lightning GPU, if you have NVIDIA GPUs, Ampere or Volta architectures, SM7 and higher, then you can run on GPUs. And this will start being beneficial if you go higher than 20 qubits, right? If you're using 1 or 2 qubits, Lightning GPU will probably not be the best option for you. But if you're working with higher than 20 qubits, then it will, right? And so these are high performance simulators that I highly encourage you to use. A lot of the research doesn't necessarily need to happen on hardware. A lot of it, big chunk of it, happens on simulators because you can do a lot more with a simulator than with a current quantum computer. Okay, this was an example of like how fast is a CPU versus GPU. This is a logarithmic scale. So you can see that if you go to say 27 qubits, it's way, way faster to use a GPU than a CPU. But if you're in the below 20 kind of level, actually using a CPU can sometimes even be better. I wanna, maybe before I go into like the next topics, I wanna see if you have questions. Oh, I see there are questions. Okay. What's technology? Okay, the hardware part is manufactured by Xanadu or another company. Great question. We do the designs, but not the fabrication of everything, right? So there are companies that are already expert in fabricating, for instance, the silicon chips. So we partner with certain foundries that fabricate the chips according to our designs. And then in-house, we test them and make sure that they do exactly what we want them to do. Somebody asks, it's like replacing the neural net layers in an ANN with quantum circuits and applying backpropagation. You can apply backpropagation, but only if you use simulators. So if you're not using simulators, then you cannot, if you're using actual quantum hardware, you cannot apply backpropagation. You need to use something like parameter shift or finite difference. Adriana is asking why TensorFlow Quantum is not integrated in PennyLane, just TensorFlow. Well, we do the quantum side of things. So like if you want to integrate PennyLane with TensorFlow, I know it works. I haven't tried to integrate it with TensorFlow Quantum. Maybe you can try it and let me know how it works. But we do the quantum side of things. So there's, as far as I know, no need to integrate with TensorFlow Quantum, but I haven't actually tried it myself. But that's a good question, in fact. Okay, great questions. Anything else? Come on. We have a couple of minutes for questions. Okay, I'll let you write your questions and we'll continue for now. We do a lot of research, and like this is something Alberto mentioned. Yeah, you want to know how it actually is working here and what we actually do. So this is an example of latest papers that we have. So we do research on quantum machine learning, chemistry, software, hardware, and architecture, right? Architecture meaning the design of their quantum computers. So this is not the design of buildings, this is how are we building our quantum computers. An example of a paper that was released like really recently is in fundamental quantum machine learning, right? So not necessarily something applied to a specific application, but let's think of quantum machine learning as a field. And we have some of the best researchers in the field here. So Maria Scholl, Nathan Killeran, and many others, they're leaders in the space. So they participated, for instance, in this particular project about quantum machine learning and contextuality, which meaning several contexts, taking it into account. We have chemistry research. So we work, and I'm going to focus a little bit more on this, but predicting properties of certain materials, for instance, simulating batteries, lithium-ion batteries. So we have specific partners, and we have a lot of people here doing both fundamental and applied research on how do we simulate chemical systems, and in particular, batteries. That's a focus, and that's something that we do very well here. Knowing where to focus our efforts is important, because we cannot do everything, so we should focus on something that is very meaningful. And that's what we have in different areas of the company. And finally, we also have a lot of research on tensor networks, for instance, also with some partners, so and like internally as well. So it's something to take into account. Like we do research on several key areas. Our fundamental research, an example is quantum machine learning, but there are different flavors of this. Tensor networks, for instance, we have some fundamental research there, and applications, we're developing the next generation of batteries, lithium-ion batteries. We also have research on software, for instance, so how to implement the quantum singular value transfer on PennyLane, for instance, and what can we do with QSBT. It kind of sometimes jumps both ways. Sometimes this research is in the middle. It's not always so easy or so distinct, the difference between where it becomes fundamental and applied. But something that is very important to take into account, and here I'm taking slides from Juan Miguel Arrazola, who works here as well. We are finding this sweet spot in the middle of what is impactful, what is easy for us to do with a quantum computer, and actually very hard to do with a classical one. So hopefully this will be one of your key learnings from today, is that if you're thinking and looking into applications, you should find this sweet spot, not letting yourself maybe get carried away with something that actually we can do very well with a classical computer. So I personally don't think that a quantum computer is going to recommend your next favorite movie. We know that classical computers can do that very well, and probably with the right level of precision. But if you want to extract more energy from a battery, then maybe a quantum computer will be better for that, right? It's something that has a huge market, a huge impact, something that is very hard to do with a classical computer, and something that we can do very well with a quantum computer. So some areas of research that our team is working on right now is quantifying exactly what are the resources needed, or how long it takes to perform a specific algorithm with a quantum computer. So not just saying this scales like n squared, but like 6n squared. So that's an interesting question. How do we optimize those algorithms that we have? So from a theoretical point of view, for future quantum computers. And if we're thinking of fundamental research as well, like if we have a future quantum computer, fault tolerant, this is a key focus that we have. How do we calculate exactly the time it's going to take, and how do we improve that? How do we find shortcuts to make it run faster? Yes, that is an example of something that we're thinking of and doing research on, right? We're thinking of spin systems. How can you use quantum computers and quantum circuits? And thinking of spin systems is a fundamental area of research that hopefully will have a lot of applications. We have some quantum data sets and some very interesting projects on quantum chemistry and spin systems data sets. So if we have a minute later, I'll show you around how you can find a lot of this information on the PennyLane website. And of course, on hardware and software and architecture, we have a lot of research into areas such as error correction, right? This is something that is key for us for the future. So where can you learn more? Please go to the Xanadu website. In the Xanadu website, you'll find everything, and in the PennyLane website, you will find the codebook. If you go to Xanadu Cloud, you'll also find it there, but it's everywhere. The codebook is a learning resource that allows you to learn the theory. So on the right-hand side, you'll find the theory, and on your left-hand side, you'll find small coding exercises. So it becomes very fun, a little bit addictive sometimes, to start solving small problems and getting the motivation to solve others. It really gets you going. If you prefer videos, if you like learning through videos more than practice, then you can find introductory videos. We have PennyLane tutorials and also more advanced ones. So QHack, which is our signature event of the year, which is starting on Monday, we record very interesting and advanced talks, and you can see them on our YouTube. For previous years and for this year, we're streaming on Twitch, but soon after, we're putting them on our YouTube. You can go to cloud.xanadu.ai, and there you can find notebooks or even install PennyLane if you want to use PennyLane locally. But I encourage you to explore the cloud because you will find a lot of material there as well. And tutorials. So this also includes code and explanation, kind of like the code book, but this doesn't have the interactive coding exercises, right? So this is more a tutorial. We often find a paper and we implement it on PennyLane. So you're going to see that the latest research, very quickly, you're going to see a PennyLane demo on this, which makes it much easier to grasp a concept and to learn than actually reading the paper. Of course, not every paper gets turned into a tutorial or a demo, but you are going to find very interesting research that is here in a cool and easy format, right? And something that you can use for your own research and to learn from. Now, I encourage you to become part of the PennyLane community. If you like coding, go to our GitHub, give us a star, a fork, make an issue. If you have questions, we have a discussion forum, which is a source where we are constantly answering your questions. So whether it's a technical question or some other question, it's a good place to go. We have a Slack, so you can go to this link here to go to our Slack. And of course, our social media, please like us, follow us, retweet us. On LinkedIn as well. We're on LinkedIn as well as Xanadu AI. And QHack. So again, if you forget everything, that's okay, but please go to qhack.ai and register. There you will, it's a really cool event. You don't want to miss it. There are amazing prizes. You will find the prizes there on the website. So go now to qhack.ai. I will, well, maybe in a second, I'll share the link on the chat. Let me share it now. qhack.ai. Perfect. And if you're wondering about how does the work at Xanadu look like, you can, like, there are a lot of jobs that are open. And if you don't find one here, you can always like find the nearest job and apply and ask questions. We have more jobs open all the time, so make sure to come and keep looking. But these are some examples. We need people that know about software, but also people that know about education, for instance. So I work with a lot of quantum educators and people on the hardware side, so electrical engineers, photonics engineers, and on the software side, again, like people are experts on different areas, right? So of course, everybody with a quantum background, right? If you're want to do quantum computing, please make. I mean, I think you're on the right path, doing a master's in quantum computing. But yeah, hopefully this will encourage you and like show you that there are a variety of roles that you can apply to, and you can work in quantum computing from different points of view and different aspects. So thank you very much. And we have a few minutes for more questions. Let me check the chat. I don't see any more questions, but please ask away.
Well,
Okay, I am gonna ask, if you're not asking a question, I am going to ask you a question. What did you learn from today? I want everybody to write on the chat 1 word or 2, but what stuck from everything you heard today? From my talk, hopefully. Oh, all
yeah,
asleep
it's a bit. I think it's a bit late, so that's why they maybe are a bit asleep and shy.
and shy.
Probably yes. I really like your talk, honestly, Catalina. Okay. Adrian is saying Penny is a good option for quantum machine learning. And in
That's
fact,
true.
we will learn a lot of things from PennyLane in the next subject, because
Oh, that's awesome.
yeah, I'm the professor more or less in charge of quantum machine learning, and I use a lot PennyLane. So, I mean, this session is perfect just as a very good introduction for that sense.
Good. Also for quantum chemistry and other areas of quantum computing. So yes, absolutely great for quantum machine learning, but also for different areas too. So yeah. It's easily usable with Python decorators. Yes, that's true. That's true. What else did we do you think, or did you get from today? What else would you like to know? Oh, okay. I'm interested in studying variational algorithms a lot, and I have a book of Maria Scholl. That's awesome. Yeah, that's a really famous book, and really glad that you have it. Okay, keep your questions coming. Now that we have 5 minutes, if I can take them too, like please keep asking your questions, but I'm gonna share my browser to show you some tools that we have and like to show you the really amazing prices that we have in QHack. Let me see if I can do this. Okay. So this is a PennyLane website. If you go to the learn part, you can learn about different topics in quantum computing. So these are like some, like some main topics of where you will be able to learn about algorithms in general, or quantum machine learning, or quantum chemistry. And here in the bottom, you will see quantum data sets. This is something new that we have, which is really cool. If you're interested in studying, say, chemistry systems, you will find a data set that contains information about say the ground set energy for different geometries, for instance. So very useful if you're trying to do VQE or like finding the classical energy or something, right? So you can get, for instance, like specific data about your chemical systems or your spin systems as well. I don't know if there are chemists in the room, but this is something new that like we're working on, and would love to hear if you have any thoughts about it. The demos are what I showed you before, that I mentioned before. So you have explanation and you have code. And at the end of the demo, you can download it as a notebook and run it locally if you want. We have several plugins. So I showed you the ones that are built into PennyLane, but you will find others. So this is like all of the different hardware and software providers that you can connect to. And the documentation is one of the favorite things about PennyLane. Everything is so like, it's easy to find and read in the documentation. So say if you go to the templates section and you say, I often use angle embedding, for instance. I want to embed my data as an angle, as a rotation. You will find a lot of explanation and code examples of how to actually use this function. That is something that I like. You have the blog where you have like recent, like, and also like how to do something, right? We have a lot of how-tos, like a little bit different from the tutorials. They're often shorter, or they can have a different format. They can be more text and less code. It varies, but also a great source of knowledge. And here on the right, you'll find support. So this is the discussion forum. You can click on new topic and you can ask a question, or you can browse through the questions that are already there. So make it super easy for you. And if you go to Xanadu.ai, you can learn more about our hardware or our software, right? We have a lot of products. You can go and learn about strawberry fields. And if you go to Xanadu Cloud, you can see what hardware is available. You can have notebooks, hosted notebooks, where you don't need to install PennyLane. It's already pre-installed here, and it makes it easier. I mean, I use it all the time. And the codebook. So the codebook is what I showed you before, where you have this kind of learning graph on the left, and you can learn the theory and the practice here. So you have these snippets of code where you can actually practice. I don't know if you're seeing my screen. Are you? Probably, hopefully. Hopefully you're seeing my screen.
Yes.
Yeah, okay. So, we have another question. Where's the question? Yes, no, someone's saying yes. Okay, so.
Excuse me, Catalina,
Yes.
I have a question. When you work with PennyLane, it's possible to use different hardware approaches. I mean, you're not just photonics, also superconducting.
Yeah, absolutely, absolutely. So let me go back to PennyLane. So here, when you go to plugins, you will see, actually, you can use Qiskit. You can use Qiskit, for instance, and you can use IBM's hardware, or you can use, say, where is it? You can use Rigetti. You can use Rigetti, and they use superconducting, yes. Right?
It's great.
I don't know if I can. This might take a couple of seconds to load, but I can maybe show you an example. But in the meantime, I will show you, this is the QHack website. For you, it will look different. You will have a button saying register, right? It's free and online, so you can just click on register and register. It has different events. So it has streaming sessions, which are these talks. It also has coding challenges, which are really good to learn and practice and get motivated. You can also meet people. Find compete in teams of up to 4 people. And there's an open hackathon as well. So in the open hackathon, it's more like open projects, and you have a week to really work hard on a specific project and get the chance to win really cool prizes. So some of the prices, NVIDIA GPUs, you have trips. You can have trips, for instance, or internships. Really, really cool prices. So hopefully all of you can try, at least register, try the coding challenges, hopefully attend the talks. We also have some workshops from our sponsors. They're giving some workshops on their specific tools. And yeah, if you want, hopefully participate in the hackathon too. Okay, so I'm gonna stop sharing. If you do have any questions, the best place to ask is the discussion forum. But if there's something that needs to be private, then you can all go through the discussion forum. You can contact Alberto and he can give you my contacts.
Yes, absolutely. Thank you very, very much, Catalina. We really appreciate from the master perspective your contribution here. We really love to have you here and hope we can continue working as well as including new PennyLane features in the master, as we already did, but even more. So thank you very, very much, Catalina, and hope you to contact you again in the future.
Yes, I hope you enjoyed it. And yeah, I really want to see you at QHack.
Absolutely.
And hopefully you will get motivated to do quantum computing and maybe even work at Xanadu.
Definitely. Thank you very much, Catalina. Have a nice day.
Good night.
Bye-bye. Thank you.